Okay, now I want to discuss a little bit about this picture you see here. So this was a snapshot from an old recording system, neural recording system, but let's say that they are all similar to this one, at least from the point of view of the functions they have. So most of the time you see windows like this. So here you have a big window where you can see the action potential of a neuron, this one. And these are all extracellular recordings. You can guess it because the polarity of the action potential is reversed. So here what you see is another plot, another chart with a, a slower time scale. So all those action potential are all of them compressed here, and you see the spikes. So these are why they are called spikes. You see also another thing, which is a sort of, let's say, background thickness, something like this. And inside that thickness it's hard to discriminate spikes. So this is somehow corresponding to this noise level. And then also another thing is that the signals recorded from the neurons, in this case, this is one channel, one electrode. So this is a spike train. You see that, sorry, it's not reporting the spike trains of a single neurons, but in this case, there are at least 3 different types of neurons, which here have been discriminated and painted with 3 different colors, yellow, blue and red. So this is because this sphere of interaction is not a perfect border, you are in or out. So you are in the sense that if the neuron is in this sphere of interaction, it will have a big amplitude, and the farther you go, the smaller the amplitude, till the point when the amplitude falls into this, let's say, background noise region. And also, for some reasons, also related to the noise, the shape of a spike is not always exactly the same for every single spike that neuron can emit. So for instance, you can see that there is a categorization. So the blue spikes here are not only all the time exactly the same. Here you see a line like this, which is a sort of average of that number of spikes that are similar each other. So those things are called clusters of spikes in the neurophysiology terminology. And one problem of neurophysiology is to try to isolate the clusters. So ideally you would like to have an impedance of an electrode which is so much tuned that it records only from one neuron. But then you might have the risk of putting the electrode in a place where there are no neurons, and if you make this capturing area having a size which is so small, then maybe you will not capture anything. So it's always a compromise. And there are methods, mathematical methods, to try to isolate a neuron. The simplest one is, for instance, to look at the amplitude, the peak amplitude. So if you see this peak amplitude for a certain neuron like this, then that one is different from another one just because of the amplitude. But sometimes this discrimination is too coarse, it's not always possible to do this. So you would like maybe to see the waveform, the entire waveform. So the yellow waveform is different from the red waveform here. So how can we give a measure of distance between waveforms in order to be able to discriminate neurons? Well, one way is to think of the waveforms, so functions, signals, as vectors. We know that we can project the vectors on a basis. We know that, for instance, we can think of a vector as, a function as the collection of all its samples. So if I take samples of a function, then I can build a vector. Now I write here a vector. Inside those the entries of those vectors, you have the values of the samples that you recorded, and then your waveform, the waveform of a single spike, will become an n-dimensional vector living in an n-dimensional space, which is the space of the samples. And then you can do things, because when you have vectors, you can compute the magnitude, you can compute the distance between the vectors. So a vector which will have exactly the same magnitude and would be will have a zero, let's say, or very low distance between another one. So if you have two vectors which are basically overlapped, it means that they are the same vector, and this happens when all those entries of one vector will be exactly the same of the entries of another vector. Basically it means that you have the same waveform. So with this idea in mind, you can compute the distance between waveforms if you can associate a vector to a waveform. And then there are many algorithms, but this is let's say an entire branch of study. I just wanted to put this seed and give an idea of what you can do also in neuroscience if you think of signals as vectors. Okay, then we move on. So here this is something that we already said. We just summarize these three things that are very important. So you have to choose the correct impedance and location according to what you want to do, use a good ground, and properly connect the reference. So we said that this thing here is bad, but this thing here is worse. So bad because you're not using the differential recording by short-circuiting the reference to ground, but this is much worse because you are using a differential recording, but if you don't correct the reference to anything, then the result is random. So we have to take care about this. Okay, so now we have to go a little bit deeper in this concept, the good ground. So to have a good ground is like having a ruler. You measure the distances of points, but you know where is your reference. If you don't know where is the reference, then you cannot measure any distance. So we have to speak a little bit about this. And to do this, we have to introduce at least some concepts of electromagnetic radiation. So some time ago I was in UK, and on the streets I found an advertisement, I don't remember of what, maybe it was a beer or whatever, and there was this guy with this face, and then because I liked it, I kept it because I think it's a good reaction. I mean sometimes if people see this kind of equation, they say, well, what is this? I mean, strange symbols. Okay, if you are a physicist, then you have a background on this, but not all of you might have it. So let's try to discuss a little bit what's the meaning of those equations in order not to have this phase anymore. So now here you have another figure. This thing is a so-called radiating dipole antenna. So it's like this. If I zoom it, then we have an alternate generator attached to two pieces of wires, so they are not connected together. They are connected to one pole and to the other pole of the generator. So when the polarity, so this generator is generating a sinusoidal wave of voltage. So when the positive is like this, here you have positive charges, and there you have negative charges. When the polarity switches, because the cycle is sinusoidal, then you have the opposite, and so you have an alternating electric field in the surrounding space, in a space surrounding this antenna, and the laws of the electromagnetism, which studied this situation with let's say great attention, also found that when you have this, you also have a magnetic field, and they are interconnected somehow. The way they are interconnected are described by four equations, which are called the Maxwell's equations. So first, second, third and fourth equation. So here we have a symbol, this delta, which is called nabla. It means harp in Greek, because of the shape. And this symbol is an operator. We already met this symbol and we said it in one dimension. It's a sort of derivative. In fact, this nabla, this symbol, the nabla of something is this thing. Where this symbol is the partial derivative. So when I say this, let's say not exactly, but I mean something like that, derivative respect to a variable. So the electric field is a vector field, so is a vector attached to every point of a three-dimensional space. And this vector is a three-dimensional vector, like this. So it comes with a x, y and z component. And then the field means that I have a vector with different angles in every point of the space. So if we go here, scratch notes. So the situation is like this. We have a reference frame, x, y and z. We can consider any point in this frame. So let's say that this is the point we want to consider. Okay. So this point P has a coordinate x0, y0 and z0. And then attached to this point we can have an electric field E, that if you prefer you can put the sign of vector in front of it, and this is a vector like this, Ex, Ey, and Ez. So the vector P is indicating which point of the space we are interested in. The vector E is indicating the direction and also the strength, because of the length of the electric field evaluated here, and we can do this in every point. Okay, so this is what we are thinking of. Now this thing is saying that if you apply this calculation here, if you compute this operation, oops, I want to change color, nabla dot, which is called divergence. If you compute the divergence of the electric field, this is a constant which multiplies rho, which is the charge density. So let's try to have an idea of what this means without doing too much mathematics. So this thing is saying that we are in the space, we consider a point, and we want to consider the charge density in the space. For instance, if I have an electron like this, let me make the electron blue, like this, then the charge distribution is a sort of spike where we have the electron and nothing and zero everywhere else. So if you want to draw rho, is something like this. So rho, now it's difficult to draw this because rho is a function of three things. So let's just say that the rho function is just a sort of spike. So the first law is considering a volume that you can draw like this, for instance, around the place where you have the charge. So let's imagine that this is a sphere around this dot. So the electron has an electric field like this. So these are the lines of the electric field. And one of the result of the calculus, this vector calculus, is that if we compute now, for reasons of clarity, let me make a positive charge, just because I don't like to have the lines pointing inwards. Let's consider here we have a positive charge. So like this. And these are all electric field. So this is the electric field. So this sphere has a cross section indicated by this circle, but has a certain surface. And one result is that if we integrate the electric field in that surface, meaning basically that we divide the surface in little portion of surfaces like this. You have to imagine a sort of patches, a sphere made by patches, and you calculate the electric field multiplied the area ds, and you summate all these things together. One result of the calculus is that this thing, which is called the flux of the electric field, is equal to the integral of the divergence of E in the volume enclosed by the sphere of interest. So this connects one thing that we can maybe better visualize, like the flux of a field exiting from a surface, with this strange thing that is called the divergence of the field. V is the volume enclosed by the surface S. If you choose a surface which is containing a charge, then this integral would be something. So say something. But if you choose a volume that does not contain any charge, this integral would be 0. So this is what the first law of Maxwell is telling us, that basically this divergence is connected to the fact that there is a charge. So this term here has a source, which is the charge. If there are no charges, this thing is 0. So in other words, the charges are the sources of the divergence of this electric field, which is connected to the flux of the field exiting for any given volume. Similarly, there is a law, which is this one, the second one, which is telling us that if we compute the same operation for the magnetic field, the result is always 0, which is interpreted in a way for which we can say that there are no sources for no monopole sources for the magnetic fields. So there are no magnetic charges. If you take a material and, for instance, you can extract electrons and move them around where you want, you can divide the positive or negative from the negative charges and make them traveling in the space. You cannot do the same thing with the magnets. If you take a magnet like this with the north and south pole and you break it in two, then you have two magnets, both of them with the north and the south pole. You can never divide the north pole by the south pole. So this law is saying this thing basically. Then there is another law which is interesting for us, which is this one. Let's have a look of it. So the third law is saying that the variation in time of the magnetic field, so this can be easily understood, it's a time derivative. So the magnetic field, if you consider it as a function of time, might be constant or might be time varying. So this thing is saying that the variation in time of the magnetic field is equal to this guy. So we have to understand what is this thing. This thing is called the curl of the electric field. So you can compute the divergence and the curl of whatever field you want. Now in the Maxwell's equation we are interested in the electric and the magnetic field. Okay, so to understand this we need to go to the blackboard. Okay. And now let's consider this situation. We have a metallic wire, and in this wire we have a current. So this current is there because there is a bigger path that now we are not drawing, and this thing is connected to a battery. So we know that there is a current, so there is a current density J, and this current density in a conductor equals GE, the electric field. This was the local Ohm's law. So there is an electric field inside the wire. But we know that a wire like this will also create a magnetic field. So let's try to draw some lines of magnetic fields. So they are closed loop, like this, all around the wire, and with the distance the magnetic field become weaker. So I draw them in a different color, like this. So the farther you go, the fainter the color, the weaker the magnetic field. So these are all the B magnetic field, and they are closed, so they go like this. They are closed because the second law of the electromagnetism says that the divergence of this field is zero. We cannot break the north and the south pole of a magnet. So now let's consider a region. I try to draw a kind of plane that is slicing this thing like this. So I draw it like this. Let's consider a sort of plane. And in this plane, those lines are crossing this plane like this, so they will intersect the plane in some points like this. And now I draw this plane here in a bigger picture. Okay. And let's say that we consider a portion of this plane, a little portion, which is little and far from the wire, in a way that all these lines, if this region is small, are kind of constant. So these are the tips. Sorry, I don't want to draw this. Okay. These are the tips of the field, of the vectors of the magnetic field passing through this surface. So these are all B in this case. Okay. So now in this situation, let's say that B is almost, let's say, uniform in the space. Now we go a little bit further. Now let's imagine that I zoomed in this picture and the entire surface of my tablet here is this place where the magnetic field is pointing upwards like this. And now let's consider a closed loop like this. A circle and this circle is made of a metallic wire, so it's a conductor. Okay, now I can think of dividing the space of this the cross section of this loop into regions. So I do I do like this. Okay. And here I have the magnetic field vector pointing like this. Okay, so the law that tells me that the curl of E is equal to minus the variation in time of the magnetic field is telling me that there is a magnetic field, we say, that circulates in closed loops like this. And by making these small loops very small, infinitesimal, then I get the definition of curl of the field. So the curl of the field is the summation of an electric field which is closed in a loop divided by the area of that loop, and then you make the limit for which the loop is smaller and smaller and smaller, which is what is written here. I go back to the slides. It's this thing. It's a theorem of field calculus that can be demonstrated. We don't do this, we are just describing this kind of thing, which gives us the definition of what is the curl of an electric field, of any field. So we read it like this. The integral of this thing in the surface, which is called the flux of this thing, so the flux of the curl of a field is the closed loop integral of the field along that loop. Let's try to see this in the picture here. So here it means that we are considering such kind of situation where we have a field which is closed on itself in a loop. Then we calculate the integral of this field on that loop, which means this multiplied a little vector which is indicating the direction of the loop, plus this multiplied that direction plus this that multiplied that direction plus this multiplied that direction. Then the theorem is saying that if we do this for every patch and we summate all these kind of things, what we should have is the integral of the electric field around the border of the path, what was called gamma. Gamma is the name of the path. So the path gamma is made of little pieces delta gamma, and we have to calculate the product of the electric field by delta gamma and summate it on every delta gamma. If we do this, now I change color, as the summation of the flux of the curl, then we have to compute the curl of the electric field in every point of the patch, and by doing so any two adjacent sides of every patch which is patching this surface will have opposite direction, so all those contributes will be cancelled each other. So if I do another path here, it will be like this, and those will have opposite direction. The only direction that will remain that doesn't cancel each other are the ones on the border. So from now this is all mathematics, but the third law of the electromagnetism, the third Maxwell law, is saying that each of these contribute that they have to summate is equal to the variation of the magnetic field inside each patch. Which basically means that if I have this situation where I have a region which is full of magnetic field lines pointing this way and changing in time, like variating up and down and up and down and up and down, and when I say up and down like this, I mean that, remember that that was a portion of this thing. It means that those lines, magnetic lines, are moving like this and like that, like this and like that, like this and like that. So they are oscillating back and forth, because there is an oscillating current that are producing them. So if we are in this condition, then there is a variation of magnetic field, and the third laws of Maxwell is telling me that when this happens I will have a curl, and if I summate the curl I will have a circulation, what is called circulation, a net circulation of electric field. And then, because if I know that if I put an electric field in a wire, because of the Ohm's law, I have a current density which is proportional to the electric field, and the proportionality is the conductivity, then it means I have a current flowing in this wire.